So here we are in section 2.4, average rate of change of a function. Average rate of change is going to be replaced when you take calculus by instantaneous rate of change. But until we have that, we stick with average rate of change. We have a question. What is your average speed if you travel 245 miles in 3.5 hours? In order to answer this question, we just want to think about the fact that distance equals rate times time, meaning how far you go depends on how fast you go and multiplied by how long you do that speed. This means we can also solve this equation here for rate by simply dividing both sides by t. So you can see it's just a basic formula there. If we divide both sides by t, we get r equals d divided by t, or how fast you go is how far you go divided by how long it takes you to do that. So in this case, if we wanted to find the average rate, we would simply take our number of miles, 245, and divide that by how long it took us to do that. That's going to give us, using that calculator that you should have. So if you don't have a calculator, get out a calculator. You will definitely be using it in this section. 70, and then as you know, we usually write that as mph, but really that's simply because the numerator is in miles and the denominator is in hours, and that's where, miles per hour comes from. So just remember that. And I'm going to take off the S there because I don't really need it because it's miles per hour, not hours. And moving on. So now we have a little graph here. Notice this graph is not linear, and that means that the rate of change, the speed here, is different. However, if we want to do the average speed of a journey here, we just have to think about how far divided by how long. So if we think about the average speed of the journey between hour 1 and hour 3, all we're being asked to do is think about this value here and this value here. So we might need to do a little bit of estimating on this, and that is okay, but let's take a look and see what we can come up with. So it looks like from our scaling here that we have 50, which would make this 150. And again, might be some estimation, but we just need to think about basically our change in our y values, which is the distance traveled. So this is the miles here. That's our distance. So if we think about basically f of 3, so if I think of this as a function, f of 3, and I subtract from that f of 1, that's going to give me the difference in the distance. So f of 3 looks like something I kind of need to just estimate. I'm going to estimate a 125, and f of 1 looks pretty legit, looks like a 50. So that's going to give me basically that the difference in distance is 75 miles. Now we need to think about time. And really that's just the difference between 1 and 1 to 3, 1 hour 1 and hour 3. So we can see that the difference there is 2 hours. So in order to find our rate here, we're going to take the 75, the difference in the y values, divided by basically the difference in time, and that's going to give us a 37.5, and it looks like this is miles per hour as well. So yay. You can do the same thing if you'd like, if you want to practice this. This is the same exact thing. Average speed of this journey, speed and rate are typically used interchangeably. So just go ahead and see if you can do the same exact thing for these two values here. All right, so my f of 4, let's see, oh yeah, that looks pretty legit there at 200. And f of 0 looks like a 0. So change in that distance is 200. And then of course the time is 4 minus 0. So that's just over the course of 4 hours. So our rate here, our average speed is, it looks like 50 miles per hour. So that's all we're being asked to do there, is basically find the change in the distance divided by the change in the time, and that's going to give us that average speed. So in higher level mathematics, we usually say rate of change. So we don't use the word speed as much as we do rate of change. But I do want you to notice here that it's really what we just did. It's just the more formal definition of it. So we have the change in y, we have the change in x. So change in y is typically, some sort of distance, depending on what we're talking about. And so that's the y values. And then we divide that by the change in x, which is, your two x values. And that's going to give you your average rate of change. So it's just a short little algebraic expression there that you just simplify. And another way to look at it is just the slope between 2 points. And those 2 points are here and here. So again, it's really what we just did, but putting it in a more formal way. So let's go back to net change. So if you remember, we're going to be asked net change and average rate of change. So remember, there's a relationship. I mean, that's really what we want to see here. So we just remember that net change is just saying find f of 3 and subtract f of 0. So we've seen that before. And then we just do basically one more step and we've got our average rate of change. So f of 3 minus f of 0, if you want to pause and go ahead and do that, you can. 1/3, and then 3 minus 3, that is 0 squared minus. And then if we put in 0, looks like I'm going to get times 9. And then that's going to just give me a negative 3. Okay. So we're talking about a function here, so the real world aspect is not as present as our last problem. So this is the net change. For average rate of change, I just need to take that negative 3. So I'll write it in 2 steps here. I'm going to take that negative 3. And I'm going to divide it by that difference, 3 minus 0, the difference in my x values. So 3 minus 0, we can see that that's negative 3 over 3, or negative 1. So that is the average rate of change. And sometimes that's, average rate of change. So you don't have to write all of that all the time. If you'd like, I suggest doing the second one, take a pause, do the second one, see if you get it right, just to cement that in your brain, and then come back and see what I do. Okay, so I'm going to write it a little bit differently. I'm just going to start with putting the word net change. So in this case, f of 6 minus f of 3. Work smarter, not harder, by understanding we already have f of 3, it is 0, so we only need to do f of 6, which is this, by plugging that into our function, minus, and again, we already did the 0, we already did 3, which gave us 0, I should say, and so that's going to give us a positive 3, and then in order to find the average rate of change, we just need to do our f of 6 minus f of 3 over 6 minus 3. So just following that formula there, we get 3 divided by 3, and that's going to be 1. So nothing too exciting, but understand that what we're finding here is really just the slope of the line between, so let's see, 0 and 3. Here's the point 0, 3, and then here's the point 3, 0. So notice those are the 2 points we're talking about in this first example here. And what we really just found, all that we found, was just the slope of this line right here. That's literally all we did. If you notice, it has a slope of negative 1. That makes sense because it is rise over run. which is a positive 3 over a negative 3, or a negative 3 over a positive 3, however you want to look at it. Point being that we found the slope of that secant line. The secant line goes through 2 points. So very similarly, if you looked at the 6, you'd be here, and then you'd just be coming down here from 3 to 6. Oh, you know me. So what we did there, all that the average rate of change was, as you can see, the slopes of those 2 lines. That's the average rate of change. So here's a more real-world example. And to be honest, it's like a lot of calculator stuff. So I'm not going to expect that you're going to do all of these, but you probably want to have them written down because we're trying to see a pattern here. So let's just start off and then we'll go from there. So we have a situation where we have an object that is falling. So you can kind of picture the idea of taking a ball and just letting it go. It's not necessarily going to drop down straight. Typically it is going to have more of a curve to it just due to various physics things. So it's going to fall, and we have a distance for that given as a function of time. So f of t equals 4.9 t squared, where f is in meters, the y value is in meters, and the x value is t, the independent variable, and that is time in seconds. So our job is to look at the rate of change of this object that's falling over the following time period. So we just need to find out how far it's fallen in between these values, divided by how long the time has been between the 2 values, and that will give us the average rate of change. So for example, in order to find it here, we find f of 4, we subtract f of 3, and then we just divide by 4 minus 3. So in the span of 1 second, we then take our function, we actually have the function f of t, and we plug in 4.9 times 4 squared minus 4.9 times 3 squared. And we find those values and we subtract them. That's a 78.4 minus 44.1. Calculator, make sure you have your calculator so that you can join in on the fun. We end up with 34.3, and then in this case we have meters as our distance and seconds as our time, so meters per second. So that's the average rate of change over that 1 second time period that the object is falling. Now what we want to do is we would want to keep going with this, and notice what's happening is the time periods are getting shorter. So we're trying to see if we see any patterns. So what I'd like you to do is to pause, and you can choose to do B, C, D, or E, to be honest. You can do any of them. And once you've done them, just pick one and do it. And in the meantime, I will write out what the work is, because they're all the same, but we want to see the pattern. So go ahead and choose one to do, so to get a little bit of practice. You're following the same pattern, so for B you're doing 3.5, f of 3.5 minus f of 3 over 3.5 minus 3. So that's all you're doing. Here you're doing f of 3.1 minus f of 3 over 3.1 minus 3. So feel free to do that. You can also do D or E or any of them, and then I'll show you what the answers are. Okay, so here is B, C, and D. So all I want you to focus on now, hopefully you got the same numbers that I did, is when we do from 3 to 3.5, so a half second difference, we're at 31.85. When we do 3 to 3.1 seconds, we're at 29.89. So notice that the difference is getting smaller between them. When we look at D, it's 29.449. So again, like the difference is getting smaller and smaller and smaller. Okay, and there's a reason for that. What it really means is that we're closing in on the true rate of change at 3 seconds. That's the bigger idea. We're going to do one more. I'm going to do E together, but I want you to see that it is simply the difference quotient. It's a version of the difference quotient because we're doing f of 3 plus h minus f of 3 over 3 plus h minus 3. So you might recognize this. So what this means is simply 4.9 times 3 plus h squared minus f of 3, which, as you probably already know, is the 44.1, since it comes back in every single one of these. And then dividing by, notice our denominator 3 minus 3, that's gone, and we're just left with h. So this is where I'm talking about that difference quotient. So what's happening here is, now we would take the 3 plus h and we'd square that, so 3 plus h times 3 plus h. So that's going to have a 9, it's going to have an h squared, and then the middle is going to be 3 times h times 2. So plus 6h plus h squared minus the 44.1, don't forget it, and then divided by h. And then you might not be surprised, I'm going to actually bring it down here. It's still equal. So you might not be surprised to find out that 4.9 times 9 is 44.1. And then plus, I have it over here, 29.4 h, and then plus 4.9 h squared. So I'm just distributing that 4.9. That's what I'm doing right now, just in case you wanted to know. And then minus 44.1 and over h. Okay, you should not be surprised to find out, because we have talked about the difference quotient before, that this and this are going to be gone. And as you can probably see, we are just left with things that have h, so 29.4h plus 4.9h squared all over h. And then, yes, we can simplify an h from each term. So we have an h that's gone here, the squared part is gone here, and then this h is simplified here. And so what we're left with is 29.4 plus 4.9h. Now, all this means is, if you know, so you could answer basically any question from this, for this problem, meaning h could be anything. So in our case, I want you to notice that in the first situation here, h was 1, because the difference was 1. Here, the difference h is 0.5. Here, h is 0.1. And over here, h is 0.01. So my point is, instead of doing all this work for all these problems, what we've done now is just come up with an expression for the difference from 3 to 3 plus h. So if you know what the difference is from 3 to 3 plus h, that's h. And then that could just be plugged in right over here, and that would give you those numbers that we got by doing all the calculations. This is a general expression for that. So that's kind of cool, but what you should notice is it's 29.4 and then plus some little bit else, meaning that as h gets smaller, you're getting closer and closer to that 29.4, which is actually the instantaneous rate of change for this function at 3 seconds. But that is calculus, so don't worry about it right now. Another thing to just a side note, this function was quadratic, so it changes, its rate of change, average rate of change changes. Linear functions have a constant rate of change, and we will talk about that when we talk about linear functions very, very soon. But it just means that their average rate of change does not change, which comes down to the fact that they have a constant slope. We'll talk about that soon.